We're going to talk about radical functions, starting with square root functions. We're going to discuss what they are and how to graph them. So a square root function is any function that contains the square root of a variable. So if there's a variable underneath the square root, it's a square root function. A radical function is any function that contains a variable under a radical. So if you think about, if you remember, a radical is the square root sign, but it's not only just for square roots. We can have cube roots, fourth roots, etc. And if you have those in your function and there's a variable underneath them, it's a radical function. So the square root function is a type of radical function. The radicand is the expression underneath the radical. So this would be a radicand. Now our square root function, in its very basic form, we talk about the parent function, is f of x is equal to the square root of x. Our parent linear function is y, or f of x equals x. So our parent square root function is y equals the square root of x, or f of x equals the square root of x. And this is the most basic version of a square root function. The type of graph is a curve. And before we talk about domain and range, I'm going to start just showing you what it looks like. If we graph this, we get points that gradually increase, but they don't increase at a regular interval. So we get that curve. When you have lines that don't increase at a regular interval, you get a curve. Okay, our domain, because we're talking about square roots and we're in the real number system and you can't take the square root of a negative number. If I plug in -1, what's the square root of -1? If we're in the real number system, we have no answer for that. So our domain is x such that x has to be greater than or equal to 0. Well, I cannot go below 0 and still take the square root. Our range, because of this, is also going to be greater than or equal to 0. I don't put an arrow on this end because I can't continue in this direction because I can't have negative x's or negative y's. Also, you may be wondering that why we're not using the negatives. So for example, the square root of 1 could be 1 or it could be -1. We're only concerned with the principal root, which is the positive one. And the reason being is because if I start using the negatives here, I'm no longer a function, because if I start plotting all the negatives, I come back down like this. And to be a function, you can only have one y for every x. So we limit these to just the principal square roots to maintain the function. Okay, if I do 4 times the square root of x, same general principle. Make my t-chart. First perfect square is 0, so I'm going to do 4 times the square root of 0, which is going to give me 0. Next one is 1. That's not 1, that's 4. The next one is 4, so I have 4 times 2, which is 8. The next one I have is 9, so 4 times 3, which is 12. The next one I have is 16, so 16. Now I want you to look at this for a second. If we come back to our very first one, we didn't actually plot these, but the square root of 0 is 0, the square root of 1 is 1, the square root of 4 is 2, and etc. And I'm doing dilations now. So now I have 2, I had 0, 1, 2, now I have 0, 2, 4, 6. We've doubled all of our y values by putting a 2 out front. And here I've got 0, 4, 8, 12, so I'm quadrupling. That's what this dilation does. So the number out front that's a whole number is going to take all of your y values and make them times that number. So I can plot this one. I have 0, 0. I have 1, 4, 4, 8, 9, 12, and 16, 16. And connect those with a curve. And if we compare this graph with our previous graph, you can see the dilation, you can see the stretching. We took this graph and we stretched it up like that. Okay, if we put a 6 on here, we're going to stretch it even more. So 0, 0, 1 becomes a 6. 4 is 6 times 2, that's 12. 9 gives me 6 times 3, which is 18. Then 4 times 6 is 24. I can't even go that high on this particular graph. So 1 gives me a 6. 4 gave me a 12. 9 gives me an 18. So you can see I've stretched that even higher. I actually can draw the curve. If we, let's just hypothetically throw in another graph. So let's just do y is equal to 1/2 the square root of x, just to show what a fraction will do. Let me put it on the same picture. Half of 0 is 0. Half of 1 gives me 1/2. Half of 2 is 1. Half of 3 is 1.5. Half of 4 is 2. So if I plot that one, I'm not going to plot 1.5. You know, that's too small. I can't really do that very well. So I'm going to skip right to 4, 1. And then I'm going to skip right to 16, 2. And if you look at this graph, you can see we're not going up very far, very fast. We cut it in half. We've smashed it down. So we shrink it. So that's just a nice comparison. Okay, so reflections and translations. A reflection is, if you think about, if you look at your reflection in the mirror, if you have, let's say, words on your shirt, they get flipped backwards. You can't read them. Well, that's what happens when you reflect a graph. It flips. Okay, it can flip the graph along the x-axis, the y-axis, or another line, and that's called a line of reflection. These are all called lines of reflection. Now, for the most part, on the square root function, we're going to be dealing with reflections across the x-axis. And so what that looks like is if here's the graph that I have to start with, when I reflect it, it'll come over here. That's an x-axis reflection. If we wanted to look at a y-axis reflection, it would do this. And if we reflected across, let's say, some line that came through like this, we'd reflect and we would do that. So you have different reflections. Whoops, I think I did that wrong. No, I think I did it right. Okay, anyway. But for the most part, like I said, we'll be dealing with these reflections across the x-axis with these particular functions. And so this is what that looks like. We take our dilator, except it makes it negative. So when I plug in x and y, draw a straight line to save my life today. If I plug in 0, I get negative 3 times the square root of 0, which is still 0. And if I plug in 1, I have negative 3 times the square root of 1, that's negative 3. And if I plug in 4, I get negative 6. And if I plug in 9, I get negative 9. And if I plug in 16, I get negative 12. Okay, and we haven't been discussing the domain and range. I'm going to go back and do that as soon as we graph this one. So I have 0, 0, 1, negative 3, 4, negative 6, 9, negative 9, and 16, negative 12. Okay, so let's look at our domain and range on these. And we start at 0 for both of these, so the domain stays the same. X is greater than or equal to 0, and the range y is greater than or equal to 0. Domain and range stay the same here too. We're still above 0, so domain, range, both of these, domain, range. We haven't changed anything. We're still having to maintain that above 0. But when we changed and we reflected, our domain is still, all of our x's are still greater than 0. I still can't plug in anything less than 0 under the square root. So my domain is still x is greater than or equal to 0, but this reflection changed my range. My y's aren't greater than 0 anymore. My y's are now less than or equal to 0. So when I reflected that, I reflected my range as well. I changed my range to being less than or equal to 0. If we look at, I forgot to define translations. I'm sorry. I'll come back and do that. Okay, so that one I did the same way. Sorry, hold it in there. So negative 4 times the square root of 0 is 0. Negative 4 times the square root of 1 is negative 4. Negative 4 times the square root of 4 is negative 8. Negative 4 times the square root of 9 is negative 12. Negative 4 times the square root of 16 is negative 16. Plot those points. 1, negative 4, 4, negative 8, 9, negative 12, and 16, negative 16. My domain, again, my x still has to be greater than or equal to 0 because I can't put numbers less than 0 underneath. But my range is less than or equal to 0 because I'm now on the bottom half of the y-axis. All right. Now, translation, if a reflection flips the graph, a translation moves the graph. So my translation is going to move the graph. So if I look at my parent, let's say my parent function is here. My translation can move it up here, it can move it over here, it can move it over here. Basically, all we do is just move around. Now, translations are when you add or subtract something to it. So we'll start with our basic parent graph again. Plug in my 0 for x, and I get the square root of 0 plus 1. So that gives me a 1. If I plug in 1 for x, I get square root of 1 plus 1. That gives me 2. 4, square root of 4 plus 1 gives me 3. 9. 16. If we look back at our originals, Square root of 0 gave me 0, so we'd have 0, 1, 2, 3, 4. Now I have 1, 2, 3, 4, 5. All I've done is I've moved up one place, one number. So if I plot this, I start at 0, 1, 1, 2, 4, 3, 9, 4, and 16, 5. Same exact shape as the parent function, but the difference is right here. I moved up 1. And that's going to change my range. My domain is still going to stay x greater than or equal to 0 because I still can't plug in anything less than 0 on that square root, but I've now moved up 1. So my range is increased by 1, or has been kind of limited. I have to now be greater than or equal to 1 because I moved up that 1 space. Okay, so that's a translation up. We can also have other types of translations. If you'll notice, this plus 1 was outside of the square root. This minus 2 is inside. And so we have to make some adjustments here. I can't plug in 0 anymore as my first x because I'd get the square root of negative 2, and that's not allowed. So what I have to do is I have to find out what to plug in here to get that perfect square of 0. And the thing that I want to plug in is 2. So when I make my x and y chart, my t-table, I need to be really cautious of that because I don't want to give myself numbers that I can't use. So my first x is not going to be 0, my first x is going to be 2. And I'll get the square root of 2 minus 2, which will give me the square root of 0. And then the next one, well, my next perfect square is a 1, so I need to plug in something that will give me a 1. So I'm going to plug in a 3. So 3 minus 2 is 1. And then my next perfect square I want is a 4, so I have to plug in a 6. And then the next perfect square I want is a 9, so I have to plug in an 11. The next perfect square would be a 16, so I have to plug in 18. So you see, we have to sometimes manipulate to figure out what x we want to give us these perfect squares. So now when I plug this in, I have 2, 0. Okay, so I have 2, 0, 3, 1, 6, 2, 11, 3, and then 18, 4. So again, same shape as the original parent function, same height and everything, but I've moved over 2 spaces. So what this has done is this has changed my domain. So if there's anything underneath the radical, so if my radicand has something other than just x in it, that is what changes my domain. And I now have to be greater than or equal to 2. If I'm less than that, I'm going to get a negative number. And since we can't have a negative square root, that won't work. My range, the lowest y is 0, so we're still at greater than or equal to 0. I have a minus 4 outside. So I can plug in that square root of 0. 0 minus 4 is negative 4. 1 minus 4 is negative 3. 2 minus 4 is negative 2. 3 minus 4 is negative 1. 4 minus 4 is 0. So I'll plug those in. 0, negative 4. So we're starting here. 1, negative 3, 4, negative 2, 9, negative 1, and 16, 0. Same shape as the parent function, but we moved down 4 spaces. So my domain is still going to stay greater than or equal to 0. And my range has changed to greater than or equal to negative 4, because negative 4 is my smallest y value. So I'm going to pause the video while I do that. Okay, so we're going to start by drawing the graph of a times the square root of x. And if you think about our parent graph, so the basic square root function goes up about like that. Okay. And if we make it twice as big, it'll go up like that, you know, and etc. And you can get the basic shape from the number that you've multiplied by. So we want to draw the basic shape based on what a is. If a is twice as big, 4 times as big, 3 times as big, etc. It starts at 0, 0, and then it passes through 1, comma a. So if a is 2, it would be 1, 2. If a is negative 3, it would be 1, negative 3. And that tells us if a is positive, the graph will continue to go up like this. If a is negative, it'll go down like that. So that's the basic starting. And then if c on the outside is positive, you start, instead of starting at 0, 0, you start at that number c. So if it was 5, you'd start up here at 5. If it was negative 10, you'd start down here at negative 10. So positive moves it up, negative moves it down. Now underneath the radicand h, if this is positive, we move to the left, which is kind of backwards from what you might think, but that's because we're under the radicand. So if it's plus 5, we'll start back here, and if it's minus 5, we start here on the right. So just to give you an idea of what I mean, I'm going to start with our graph of negative 3 times the square root of x, which we've already done when we were plotting points. And if we go back and we look at that, well, we can look at the table and see that we had 0, negative 3, negative 6, negative 9. But we don't have to plot all that. I know I'm going to start at 0, 0. I know I'm going to go through 1, negative 3. And that's going to give me my basic idea of where to go from here. My general shape, I'm having a hard time with this curve. It's going to be like this. Had a hard time with that one for some reason. Okay. Negative 4, I'm going to start at 0, 0, and I'm going to go through 1, negative 4. So it's going to be even taller, like that. Okay. X plus 1, so we move up 1. So we're like that. We start at 1 instead of at 0. Minus 2, we're going to move to the right 2. So we start at 2 instead of 0. Minus 4, so we're going down here. We start at negative 4 instead of 0. And then this plus 3 is underneath, so we go back 3 instead of starting at 0. If we combine transformations, so we have more than one thing happening at a time, and I'm going to first plot points and then discuss how you can do this without plotting points. So here we have the square root underneath by itself, so I can plug in 0, and I get negative 2 times 0 plus 1, so that's 1. And plug in 1, so I get negative 1 plus 1, so that's negative 1. I can plug in 4, So -4 plus 1 is -3. 9. That gives me -6 plus 1, so -5. 16. So -8 plus 1, -7. So I have 0, 1, 1, -1, 4, -3, 9, -5, and 16, -7. So that -2 flipped us over and doubled us, and then we shifted up 1. So if we wanted to plot that without plotting the points, we'd have to take all of those into account. So if I go through and I take those out, and I want to graph this, the +1 tells me to start here. The negative tells me to go down, and I need to go down and be twice as high, or twice as big. So I could do it that way. Now, 1/2, we talked about that a little bit. So I can still plug in 0, and I get -1. If I plug in 1, I get -1/2, which is okay, but not very fun to graph. If I plug in 4, I get 1. If I plug in 9, I get half of 3 minus 1, so that's 1.5 minus 1, so that's 1/2. If I plug in 16, I get half of 4, which is 2 minus 1, so that's 1. So what I'm going to do is I'm just going to plug in those. Half of 2, which is, oh, sorry, this should have been a 0. I'm going to plug in these numbers, the -1, the 0, and the 1. So 0, -1, 4, 0, 16, 1. So I shifted down 1 and I squished to make myself shorter because of the half. Here, I'm going to go ahead and try to do this without plotting points. So this -2 underneath means that I'm moving 2 places to the right. So that's where I'm going to start. That negative means I'm going to flip. And this 2 means I'm going to double. So instead of being, the normal shape of a parent graph, I'm going to be twice as fat. Okay, so that's how you can combine those. And like I said, there's 2 choices. If you want accuracy, if you're looking for specific points, you're going to want to go ahead and do a T-chart. If you're just looking for the general shape, you can combine your translations, dilations, and reflections and just draw a general idea.